Hey, good afternoon, everyone. Happy Friday to all of you. My name is Dan Painter. Once again, I will be the host for today's web conference titled House of Resistance. For those of you that are joining us today for the first time, welcome. Up on the screen is a schedule of web conferences that we will be conducting through the early portion of March. Those that are rejoining us from last week, welcome back. And again, today's topic is House of Resistance. So with that, we'll get started. Some of you may be questioning the title of the web conference, House of Resistance, but basically what it boils down to is this is kind of a real easy to use and a very easy to understand pump sizing tool. We've had a number of seminars that we've conducted here at our factory, along with a tremendous number of regional type seminars. And over the years, it became very apparent, at least to me, that one weakness that I believe exists within irrigation for the most part, and please don't anybody take this personally, but one weakness that does seem to kind of stand out is folks' confidence in sizing pumps, or when it comes to sizing pumps. I've talked to contractors that have been to pump companies, manufacturers, and they've went through this so many times, and they still seem to struggle with, the formulas and the terminologies and things that have been used historically and traditionally in sizing a pump. So hopefully today you'll find that this House of Resistance just kind of turns the light bulbs on for you a little better. And as always, if you are interested in a copy of this presentation, or would like just a resource to have to go to, please feel free to get a hold of either Jamie or Tiffany here at Flint Walling, and they'll be happy to meet your requirements there. When it comes to sizing pumps, I think the first thing I would reiterate to everyone is there are a few things that you need to know. They're not 100, not 10, not 20, not 15. There are 5 things, and only 5 things, that you really need to grasp information on when it comes to sizing up a pump for irrigation. Those 5 things now listed on your screen include at the top gallons per minute, which oftentimes expressed in the terms GPM. Below that, we have pressure, and that again is going to be in PSI. Then we go to lift, and on to elevation, and then lastly, friction loss. So these are the 5 things that we are going to ask about when it comes to sizing a pump. And I would like to, before we actually implement the model of the House of Resistance, I'd like to just go through and let's just talk briefly on each of these 5 areas of information that we need to acquire. We'll start off talking about gallons per minute. You know, it's not inconceivable, obviously, that a irrigation system could have multiple zones or will have multiple zones. And I will tell you, and I will also make a confession, that today's presentation was done a lot for my benefit, so meaning that I've rounded some numbers off just to make this flow easy and be better for you to grasp, et cetera, et cetera. But when you look at the illustration that's on your screen now, this is in very, very simplistic terms. We're showing that we have 3 zones. Now, these zones only have rotors in it, but obviously in real life there can be other types of devices used for irrigation. The bottom line when it comes to irrigation and looking at these zones and looking at gallons per minute is you always want to size your pump based on what we would call peak flow rate or peak demand for water. So when we look at this illustration, for example, we've got 3 zones there. Zone 1 has 4 rotor heads, Zone 2 has 5, and Zone 3 has 3. If we were to assume, and this is where the easy math comes in, but if we were to assume that each one of those rotors required a flow rate of 3 gallons per minute, and I know this number is not kept secret. Most of the manufacturers that manufacture rotors and other devices, they don't keep that information a secret. They'll tell you what that device needs as far as not only gallons per minute, but pressure, so that it operates in its optimal mode. But if we were to do the simple math, and if each of these rotors are worth 3 gallons a minute, that would mean that then zone 1 would require a flow rate of 12 gallons per minute, while zone 2, because of the 5 rotors, it's going to require a flow rate of 15 gallons per minute. And then lastly, zone 3, the little guy down there at the bottom, there's only 3 rotors over in that zone, so the flow rate requirement there, again, based on 3 gallons per minute each for these rotors, would only be 9 gallons per minute. But this does give us an opportunity to kind of look this irrigation system over, and I think most of us can very easily determine which one of these zones do we want to size this pump for. And obviously the zone number 2, because it's got the greatest demand, that's the one that we're going to size the pumps for. So when you're asking someone how much water do you need, you really want to kind of dial that down to, what zone is going to require the most demand of this pump, so that we make sure that this pump is sized to meet that peak flow demand. And so I just wanted to cover that gallons per minute there on the screen. We'll move to the next one, which is pressure. And, when we talk about pressure and having, again, a lot of history and experience in conducting educational seminars for contractors and distributors alike, one of the things that I find out there, and you may or may not agree with this, but I think for the most part the industry seems to buy into this, is that if you can get 50 psi, if you can get 50 psi at the device where you're actually, distributing the water, not necessarily the pump, but wherever that zone is that needs the water, if you can get 50 psi out there, I think by and large most people find that to be adequate. Again, that pressure can go up or down based on, based on desire. So, but we need to know what pressure someone wants to operate their system at. And so for this example, I'm just throwing 50 psi up there just as, again, for an example. We're now going to move to number 3 in that list of 5 things that you need to know. And number 3 had to do with a term called lift. I want to spend just a moment or two talking about lift. And hopefully these slides are transitioning for you at the same rate they're transitioning for me, so that I'm not talking about a slide that you're not seeing yet. So I'll kind of pace myself with these slides just a little bit. But when we talk about lift, when we describe what lift is, I want you to understand that when we talk about lift, it is the vertical distance from the water source to the inlet of the pump. Again, it's the vertical distance, not horizontal. That pump could be sitting, 50 feet away from the edge of this channel here. I don't care about that 50 feet. What I do care about is how far is it from the surface of that water to an imaginary line that would represent the inlet of that pump. And again, that would typically be measured in feet. The other day I was doing a seminar, and a guy asked me a question. He says, well, are you sure you don't want to measure that from the foot valve, which typically is submerged down below the water level? And the answer is no, we don't want to measure it from there. As we've talked about, we want to measure that level of water measure that lift from the level of water, wherever that's at, to the inlet of that pump. What I did to help maybe explain to this gentleman why I wasn't too much concerned about where his foot valve was located, that could be 8 feet underneath the water level, I don't know, but the way I kind of explained it to him is this way. Let's just suppose you have a glass of water, and the water level in the glass is almost all the way to the top. You put a straw down into that glass. My question is, where would the water level be inside the straw? Well, the correct answer is the same place that it is in the glass, right? I think we're all quite aware of that. so that when you put your finger over the top of that straw and you lift it up, you retain that level of water inside that straw. So the water level inside the straw is at the same level that it is inside the glass. That would be no different than a drop pipe that's going down to a foot valve. When you suck on the straw, when you draw liquid out of the straw, you're really only having to lift it from the level of where it's at to your lips. So again, when we talk about lift, we're only concerned with how far is it from the inlet of the pump to the surface of the water source vertically, measured in feet. So sometimes that water source could be a well. We would want to know how far is it from, again, the inlet of the pump down to the water level in the well. If someone may be pulling water from an underground cistern, that pump's going to have to lift some of that water up out of there before it can pump it. And so we need to, once again, know where the water level's at, or if it's simply pulling off of a lake or a pond. All of these applications will have some form of lift, more than likely, involved. That pump's going to have to pull that water up from a lake, from a cistern, from a well, from whatever the water source is. It has to pull that water up into the pump housing before it can then begin to deliver it to where you want it to be. So those applications would always have some lift involved. There are, however, a couple of applications that would not have lift involved. And again, when we talk about that, we're simply talking about vertical. I really want to make sure that gets emphasized, that we're talking about the vertical distance. But other applications that really there would be no lift is, let's suppose that a pump's being installed on a municipal water system or a city water supply. And the suction portion of this pump is being fed by a city water. And in that application, perhaps it's just being used to boost pressure and provide water to the various zones. But it doesn't have to lift water anywhere because that water will be supplied to that pump under pressure from the city. If it's an above-ground storage tank, and this is a fairly common application that I've seen, and the pump's basically drawing water out of the bottom of one of these storage tanks, that's all gravity fed into that pump. Some people refer to both these applications as flooded suction. In other words, water is being provided to the pump without the pump having to lift that water and draw it into the housing so that it can pump it beyond that. So just a few applications. So when we're talking about lift, how far is it from the pump to the water level? That's what we're asking about. City water supplies, obviously, there's no lift. An outside storage tank, when the pump's hooked up to the outside bottom of that tank and the water's being gravity fed into the pump, there's no lift. So let's go to the fourth one, which is elevation. In other words, how far is the highest spot in your irrigation system? How far is it? Because if the pump has to pump water uphill, up an incline, if the pump has to overcome some elevation, we have to know that when we go to size our pump. So again, elevation is going to be the vertical distance, not the horizontal distance, from the outlet of the pump to wherever the highest zone in your irrigation system would be. So that's what's referred to as elevation. I will tell you, folks, that here in Indiana, we don't have elevation. We are flat as a pancake. I think that's why perhaps this time of the year we can see wind chills at 15, 20, or 30 below zero, because we have absolutely nothing as that wind comes across this great state to stop it. In fact, I had a dog run away when I was a young child. And 3 days later, I could still look out there and see it. You know, that's how flat we are. But again, when it comes to elevation, you either have it or you don't have it. So it basically boils down to some kind of a guesstimate. You know, you got to go up 20 feet, you got to go up 150 feet, whatever that is. But when we look at both lift and elevation, they will both be determined and measured in feet. And just one last time, the lift is from the inlet of the pump to the water source. How far is that vertically? And the elevation is how far is it from the outlet of the pump to the highest level within your system? How far is that in feet? The last one that we're going to look at is friction loss. And basically, even though friction loss doesn't really play a huge role in our pump sizing and our pump selections, it's still something that the pump has to overcome. And so therefore, we're not going to neglect friction and friction loss. And, you're going to have friction anytime two surfaces come together. Now, I've got a little cartoon type illustration up here. Obviously, if you were skiing down a hill with snow, you're going to move a lot smoother and a lot faster than if you try to come down that hill with no skis and no snow. So it all has to do with friction. One of the things that have kind of intrigued me, and particularly with this last Olympics that we went through, and I guess that had to do with swimming. It amazes me at that Olympic level to the detail that these athletes take in an effort to reduce friction. Many of them shave their heads. Many of them will wear some type of a wetsuit, or shave their legs. Basically what they're trying to do is they're trying to minimize that friction as the surface of that water crosses the surface of their body. And anytime, again, two surfaces come together, there will be friction. In our applications with pumps, that occurs typically inside the piping. So as the water leaves the pump and it travels through the pipe, it will be rubbing along the inside walls of that pipe, which creates friction, which slows the process down. And so when we look at friction in a pumping system, we have to understand that there's some things that can predicate or dictate what this friction is going to be. Obviously, the amount of water that you're going to flow through the pipe will play a factor in how much friction you're going to have, how fast you're moving it through there. And the other thing that will dictate the amount of friction that we can lose in a pump application is the size of the pipe. Obviously, the smaller the pipe, the greater the friction loss. So, and the length of the pipe. The longer the pipe, the greater the friction loss. So, though this is not something you want to do, if you would want to establish a tremendous amount of friction, I'll tell you how to do that. First of all, run all of your piping in 1/2 inch. That'll give you a lot of friction. And don't worry about how far you run it. Run it as long as you want. Make it hundreds and hundreds and hundreds of feet. And you can get a lot of friction loss through there. And oh, by the way, use galvanized. That inside wall of galvanized plumbing is nowhere near as smooth as inside plastic or PVC type of pipe. So again, those aren't things. We want to minimize friction, not maximize it. But when we look at that whole scenario, the smaller the pipe size, the greater the friction loss. The longer the length of pipe, the greater the friction loss. And finally, the higher flow of water that you flow through a pipe, the greater the friction loss. So again, when we go back to these 5 things, gallons per minute, pressure, lift, elevation, and friction loss. How does this all pertain to the house of resistance? Well, I'll show you. When we talk about the house of resistance, we're basically going to plug one of these into each room of our house. Now, I put the gallon per minute up there on the chimney because that's going to be a number that we establish and we're going to hang on to. But this is not a big house. It's relatively small. It's only got 4 rooms. And those 4 rooms have a name. Each room has a name. There's one there for pressure. There's one there for lift. There's one for elevation. And then again for friction loss. So let's build a house and let's size a pump. When we go back to one of the previous slides I showed you, the one that had the various zones in there, I think we can all agree that in this particular application, in this particular example, we need to make sure that we give consideration to zone 2. It is the zone that requires the highest amount of water in gallons per minute, and in this case it's 15 gallons per minute. So what I would suggest that we do when building the house of resistance is we take that 15 gallons per minute and we shove it up in there in that chimney area. So we've got that number up there, that 15 gallons per minute. The next question was, how much pressure do you want? Well, we showed a slide on this too, and going on the premise that 50 psi is adequate and satisfies everybody's, demand. Again, it can be higher than that, it can be lower than that. I got to pick a number, so I picked 50 psi, and so we're going to take that 50 psi and we're going to place it in our pressure room. The third thing that we talked about, as far as the 5 things you need to know, remember we talked about lift just a few minutes ago. And let's just suppose that this particular job that we're sizing this pump on, we've just determined it's going to require 15 gallons per minute, and we've determined that we want that at 50 psi. Then the next question is, do you have any lift at all? If the answer is yes, then the question is how much? Well, not a lot, maybe 5 feet, but that could be 10 feet, that could be 15 feet, that could be some other number. I'm picking a number here. So let's just suppose for this particular application, we have 5 feet of lift. So I think you're catching on what we're going to be doing here with this house. We're going to put the 5 feet of lift in the lift room. The fourth question that I'm going to ask is, do you have any elevation? The answer is typically yes or no. If there is no lift, if there is no elevation, then we will put a 0 in those respective rooms. But for our application here, we do seem to have a little bit of elevation involved. Not a lot, but we do have some. It amounts to about 25 feet. And so we're going to go ahead and we're going to drop that 25 feet of elevation into our elevation room. So there you go. So we're almost done with this house, almost. The last thing on here is friction loss. And friction loss can often, again, can be determined by the pipe size, the length of pipe, and the amount of water that you're flowing through the pipe. Because once you have those 3 pieces of information, a friction loss chart is very, very easy to disseminate. In fact, let's just imagine that this 15 gallon per minute pump that we are sizing right now, let's suppose the contractor has informed us he is using 1.5-inch PVC pipe and he's got about 200 feet of it involved, okay? So 1.5-inch pipe, 200 feet, and 15 gallons per minute. When we look at a friction loss chart, I'll pull one up here for you real quick. If you look on the left-hand side of that chart, it indicates flow rate in gallons per minute. Well, you kind of scroll down through there with your finger till you locate the one that applies. Well, 15 gallons per minute is what we've all been talking about. So you put a finger or an arrow on 15. With the other hand, come to the top of the chart. This happens to be for PVC pipe, and I think most of these friction loss charts, they'll indicate the type of pipe at the top of each one of them. This happens to be for PVC, and as you can see, they show sizes ranging from 3/4 inch to 1 inch to 1.25 inches, 1.5 inches, and up to 2 inch. Well, we've all determined that we were running 1.5-inch pipe. If you recall, we were going to run 15 gallons per minute through 1.5-inch pipe, and we've got 200 feet of that pipe. So you come down from 1.5 inch, you come over from 15, and you intersect in a box. In this particular box, we are showing 1.53 feet. When you look at friction loss charts, you can find them in a variety of different ways, but feet is one of them. And so this shows 1.53 feet. But like most friction loss charts, they will have a notation somewhere near the chart that says note per 100 feet of pipe. So when I look at this, I see 1.53. Well, I immediately, I'm going to round that off. I'm just going to make it 1.5 feet. It just makes it easy for the math. But that 1.5 feet is for 100 feet of pipe. And a slide ago, we determined we have 200 feet of pipe. So my question to you is, what do we need to do with that 1.5? I'm sure most of you in your mind thought, well, if that's per 100 and you've got 200 feet, I suppose we'd have to double it. And that is true. So we're going to take that 1.5 and we're going to double it. In so doing, that number becomes a 3. And so we are going to drop that 3 into our house of resistance. So right now we've built this house. And that's how easy it can be. And but we do have a fly in the ointment, and this is where I hope I don't knock you overboard or lose you here, okay? There is a fly in the ointment. Let me explain the fly to you. We have lift expressed in feet. We have elevation expressed in feet. And we have friction also expressed in feet. The fly in the ointment is the pressure. You may recall from one of our first slides, pressure is expressed in pounds per square inch, or PSI. Well, my whole house is based on feet, not PSI, but I've got this pressure up there that's in PSI. So what do I do with that? There is a formula that you can use to convert that pressure to feet. And basically what we'll do is we'll take that 50 PSI and we're going to multiply that. We're going to multiply that times 2.31. So whatever that pressure is, it could be 40 pounds, it could be 60 pounds. In our case, it's 50 pounds. Whatever that pressure is, we want to always multiply it by 2.31. And in so doing, we now have established feet for our pressure room of 116. So this house is completely built. All the rooms are full. And here's what we end up doing with our house. We take the feet of the 4 rooms that are in our house, and we're going to add them up. All right? We're going to add them all up. So we're going to take the 116 that we got out of the pressure room, add it to the 5 out of the lift, to the 25 feet out of the elevation, and the 3 feet out of the friction. I spoke to you earlier, and I said friction doesn't oftentimes play a huge role in our pump selection, but yet we do not want to neglect it and overlook it. Where it will play a huge role is if pipe's undersized, or it has a whole lot of length to it, then all of a sudden your feet can climb fairly rapidly. But in this case, we're running 15 gallons a minute through 1.5-inch pipe. We're going to add all those up, and we come up with 149 feet. We are at a portion of our discussion right now where we have the 2 numbers we really need. Those 2 numbers being gallons per minute and feet. We have established that we need 15 gallons per minute, and our house is 149 feet. When you end up with those 2 numbers, please listen to me carefully. When you end up with those 2 numbers, you can now go to any pump sizing curve and make a pump selection. This illustration shows a pump sizing curve. Along the left-hand side are feet. You can see this particular pump curve ranges from 0 to 250 feet. Down at the bottom and running along the bottom is flow rate, expressed in gallons per minute. And again, this ranges from 0 to 60 gallons per minute. This chart can vary and will vary with various size horsepowers or categories of pumps. But the way we use the friction loss chart is we're going to locate our feet on the side. Well, I don't see 149 up there, but 150 is really close to it. And I don't see 15 down at the bottom, but I'm smart enough to know halfway between 10 and 20 is going to be 15. So like we did with the friction loss chart, we are going to run up the chart from the 15 gallons per minute. At the same time, we're running across the chart at about 149, 150 feet at that 150 feet level, and we're going to intersect. And it's where we intersect that we can make our pump selection. Now again, I've done this so that the math works out, so it's very easy for me to illustrate to you how to use this method of sizing pumps. But when I look at that intersection, it's hitting right on a curve, which happens to be a 2 horsepower, 2-stage centrifugal pump. Bingo. Done. We've sized a pump. And maybe for some of us, this is the first time we've been through something like that. But just to help cement it and help, let's just do this exercise one more time. I look at the clock. We still got a few minutes to go. We will be probably ending a few minutes early today. But I want to run through this house of resistance one more time to make sure that we didn't go through it maybe too quickly for some of you on the first go around. So let's go ahead and size up a second pump. All right, so the first thing we're going to establish is gallons per minute and what is the peak flow. Well, the guy comes back and he says, you know, I've got a zone that's got 8 rotors in it. And again, let's use the premise that these rotors require 3 gallons per minute each. So you can do the math just as easy as I can. If this is the largest zone in the system, then we're going to need to size that pump for 24 gallons per minute. So what do we do with that 24? Well, we shove it up there in the chimney portion of this house because that's the number we're going to hang on to. All right, now we'll move on to the next one, which was pressure. You know, how much pressure do you need? How much pressure do you want? Well, let's just suppose in this particular application, they're asking for 60 psi. Now, we have a room in our house called pressure. And I think you saw just a few minutes ago that we have to do something with that pressure, really, to convert it to feet, to add it to our house. So let's just go ahead and knock that one out right now. And I guess a question to you is, do you remember, do you recall what we have to do with the pressure, irrespective of what that pressure number is, whether, again, it's 40 or 60 or 80 or whatever it is? You recall what we need to do. You need to take that number times 2.31, and that's what converts it to feet. So I've taken my pressure of 60 psi, I've multiplied it, it's 139 feet, and so I'm going to go ahead and drop that 139 feet into my room titled pressure. All right, let's move right down the list, continue moving. The next question I would have for you or whoever I'm sizing this pump for is there any lift or elevation involved? And again, the answer is yes, no, some, little, but we want to try to get to a point where we can state, you know, well, approximately how much is there? Let's just assume for this application that we have 10 feet of lift this time, not quite the elevation, only 15 feet of elevation. And so what we'll do is we'll take that 10 and that 15, and we're going to go back to our house, and we're going to drop those two numbers into our house. So now we're left with the last room of the house, that being friction loss. We already know we're going to be running 24 gallons per minute. All right, so let's go on to this next one. This particular application is also going to use 1.5-inch pipe, but we're going to run 300 feet of it, not 200 like we did before. So again, when you come down the left-hand side of this friction loss chart, there is no 24 on there. What I've done is went to the next highest number. In this case, it's 25. And I would probably suggest if you ever fall between two numbers, if you want to be conservative on your sizing, go to the next highest number, not necessarily the closest number, but the next highest one. So for this illustration, we have a demand for 24 gallons per minute. I'm going to put my finger on 25 gallons per minute. I'm going to come across the top of that chart. I'm going to locate my pipe size. Once again, it's 1.5 inches, 1.5-inch PVC pipe. I run over from 25. I run down from the 1.5. I intersect in a box. Hopefully you can see what that box says. It's what I'm reading here on my screen is it says 3.95. Again, I go right back to my rounding mode of thought, and I'm just going to make that a 4. But we have 300 feet of pipe. And one thing I told you a few minutes ago is most of these friction loss charts really state that in per 100 feet of pipe. So if I've got 300 feet of pipe and I've got a 4 showing up here on my friction loss, what do I need to do with the 4? Well, I got to triple it, right? I've got to multiply that times 3. So I'm going to multiply that 4 times 3. I come up with 12 feet. And so when I go back to my house and I fill in my friction loss room, I can drop in the number 12. I think you probably recall by now what we have to do with this house that we're at this point. And the next thing is we're going to add up the feet that are in the house. So I take the 139 out of the pressure room. I add it to the 10 feet that's in my lift room, to the 15 feet that's in my elevation room, along with the 12 feet that I've got with friction. And when I add those all up, I come up with 176 feet. Now, once again, we're back to those 2 magical numbers that we all strive to get to in order to size a pump up. So I'm going to go in at 24 gallons per minute, and I've got 176 feet. So when I go to the friction loss chart, or no, I'm sorry, the pump performance chart, I guess I didn't get this slide quite finished, but I'll walk you through it. 176 feet. I see 175 listed on here, so that's pretty close. You know, it may just go a hair above it, but you know, 175 is close enough. 24 gallon a minute. Well, if you come down from the bottom of that chart and look down there, I'm going to probably put my finger somewhere between halfway between 20 and 30. That'd be representative of 25. That 25 is close to my flow rate requirement. That 175 feet is close to my flow rate requirement. So I'm going to come up from the 25. I'm going to come over from the 175, and I'm going to intersect in a box or somewhere on that chart. Right there. Bingo. That fits that particular pump curve perfectly. That would be a 2 horsepower, 3-stage centrifugal pump for that application. Now, once again, and we're winding this down, I put the numbers together so that they would work out as you see on this chart. It's not uncommon. It's not uncommon that you may end up somewhere in the middle of this chart. And you're not on any of the performance curves running through there. You're in between 2 of them. That can happen and will happen. And when it does, you always want to go to the next pump that's above that mark on the chart, not the ones below it. Because if you go down and you pick up a pump curve below where you're hitting, you're not going to get the performance that you need in order for that pump to be sized properly for that particular job. So the house of resistance makes it, I think, a little easier to understand how to size a pump. It I think makes it easier to come up with the with all those things that we need to take into consideration. And I'm going to end the conference this way. If I were standing in a classroom and you all were sitting in front of me, and we already made the determination that we needed, let's just use our last example, 24 gallons per minute and 60 psi, I would walk over to a centrifugal pump. I'd place my hands on the centrifugal pump. I would look at you and I'd say, okay, what you're telling me is you want 24 gallon a minute and 60 psi, correct? And the response is yes. My question then to you is, okay, where do you want that 24 gallon per minute and 60 psi? Do you want it right here with this on this pump that I've got my hand on? Or, and I'll walk all the way across the front of the training center, do you want it over here where your furthest zone or your greatest demand for water is at? Where do you want it? Well, everybody always responds back, we want it at the rotors. We want it at the zone. And my response is, so you don't really care what comes out of the pump, just as long as you're getting your 24 gallons per minute and your 60 psi where you want it at the zone that's located somewhere over here. Yes, that's what they want. Everybody says, yes, that's what they want. And I said, okay, you need to understand one thing. In order for that pump, which is over on that side of the room, to deliver that water and that pressure that you want over here where I'm standing, you have to understand that that pump has to overcome resistance in order to get that water over there. Just like the swimmer going through the pool has to overcome resistance. Just like the skier coming down the ski slope, these guys will wax those skis up to overcome resistance. A pump has to do the same thing, and that's why we refer to this house as the house of resistance, because it contains those elements that that pump must overcome. So with that, again, I appreciate you taking time and sitting in. I think this is a very valuable tool. I think it's an easy tool. I have sat through countless seminars, and you can just see the light bulbs going off. And you know, it's a great thing when we can learn something of any given day. It's a great thing. I think the day you don't learn anything is the day they'll probably be planning you. So with that, I'm going to put the schedule back up. We're going to be doing a repeat of these two web conferences that we've done the last 2 weeks. We will be doing these again in February. We'll do the overview on the 3rd of February. We will do the House of Resistance once again on the 17th. And then also another repeat into March. And hopefully after March, we're in the season for selling pumps. And so with that, and the last thing I would encourage is, particularly for a lot of you distributors, if you have some key contractors you think would benefit from sitting in on a web conference like this, get them registered, let them register, and they're more than welcome to sit in on this as well. But with that, I wish you a happy weekend. If you travel, travel safe, and until next month, good selling. Thank you very much.